Hi guys, BuildZoid here, and today we're going to be taking a look at the voltage frequency scaling behavior of the P and E cores of the 12900K that I have. Thank you to Gigabyte for making all of this testing possible, as they provided the motherboard, the CPU, and the memory kit. I tested on a Gigabyte Z690 Aorus Pro. I used a 240mm AIO for cooling. We're just running Cinebench R20, and I'm not running it like for very long run time, so the cooling capacity of the AIO isn't that important. Also, I was using Arctic MX4 thermal paste, so the reason I bring that up is I do believe you might benefit with liquid metal on top of the IHS of a 12900K, because the heat density seems to be quite high, and I will be testing that in the future, but for now I haven't tested that yet, so yeah. Anyway, let's talk about the P-core scaling behavior, because the P-cores are, like, my favorite part of a 12900K. Like, they are insanely fast. Like, let's just cover this first, I think, just how insanely fast the P-cores are, which isn't the scaling behavior. But at 5 gigahertz, right, the P-cores get 7,930 points in Cinebench R20. At 5.2, they get 8,233. And at 4.7, like, they get these kinds of, like, you get from, like, mid 7,000 up to, like, a little over 8,000 points in Cinebench R20, depending on, what frequency you're at. For comparison, a 10900K, right, a 10-core CPU from Intel from, like, a year ago gets... like, in order to get those kinds of scores, you need to be running in excess of, like, 5.5 gigahertz, right? Because here's the first, like, 7,400 points at 5.7. Now, evidently, the efficiency there isn't that great, because we have Quick Mu over here at 5.7 with a 7,600, but that still loses to a 4.9 gigahertz 12900K, and I'm like, this isn't some super crazy optimized benching OS that I'm using here. So, like, the P-cores are ridiculous. And then also, if you want to go over 8,000 points with a 10900K, you're looking at like 6.5 like north of 6 gigahertz on a 10900K, right? So 8 P-cores at totally cool, like totally normal frequencies are faster than 10 Comet Lake cores doing around 6 gigahertz, which is insane. So I absolutely love the P cores because they have so much single-threaded performance. It's just so much freaking single-threaded performance. There's nothing else to say. It's great. So yeah, I'm a big fan of the P cores. They're insanely fast. And honestly, they get pretty decent efficiency if you're not running them at, like, really high voltages. I'm a really big fan of the P-cores. Now then, let's talk about the actual scaling behavior. So the main thing you can see from these results, and the way the testing was conducted, is I just went in 50 millivolt voltage steps, and whatever ratio would run is whatever ratio is over here. The reason I went with this test methodology is just it saves time. Like, the more detailed method would be to go and check what is the lowest passing voltage for each given frequency. The problem with that method is just it takes forever, and there's a lot of margin for skewing the results, right? Because if you're going from minimum passing voltage, things get a bit like there's more judgment to it than, like, does the ratio run or not, right? With this kind of step size. Now, this would work, this would generate a lot more useful data if I had more 12900Ks to test. But even then, it just gives us a pretty good idea of what kind of behavior to expect in general, I think. Though it is worth noting that, as far as I'm aware, the 12900K that I have is pretty good, as a lot of chips won't necessarily even do 5.2 gigahertz for Cinebench R20 on ambient cooling. So yeah, I don't know, like, I've not confirmed that myself. I don't bin CPUs. I have one chip. It's a Intel, review kit CPU, which, as far as I know, those should be, from what I've been told, those aren't generally very special. But yeah, it's not like I have some crazy bin CPU here, but evidently I seem to have gotten lucky with the chip that I have. Anyway, so Yeah, and the thing that we can notice from the scaling behavior is that if you do not get whatever frequency you're aiming for with like less than 1.3 volts dye sense, you are not hitting that frequency, right? Like, because we have pretty good scaling up until 1.35 volts, which the reason this is estimated dye sense voltage and not like measured dye sense voltage is because currently hardware info does not have support for the RAA 229131 voltage controller, so there's no way to get a dye sense voltage reading that isn't incredibly tedious, and as I've mentioned before, I am very lazy, so instead I've worked backwards from how the behavior of the Ultra Extreme LLC, which has no V-droop, to figure out roughly what voltage we're at here with the high LLC. Um, Anyway, so yeah, with if you don't hit whatever frequency you're aiming for with less than 1.3 volts of dye sense voltage, you're probably not going to hit that frequency ever because the scaling just hits a brick wall, mostly due to the, temperatures getting really out of control pretty quickly if you keep raising the voltage. Um, so yeah, with 12th gen, I'd say the limiting factor is just going to be your cooling, which is why I also said, liquid metal might be an interesting thing to consider using on these CPUs. Also, just get the biggest cooler you can. Just yeah, honestly, I'd say custom loop. This is one of those CPUs where I think I'd go for a custom loop. Like I'd have like a 360 millimeter radiator dedicated just to the CPU alone. Um, but yeah, and then also I'd very much probably go with liquid metal between the IHS and the CPU itself. Well, I mean IHS and the water block. So not gonna go all the way with like a D-lid. Um, but yeah, so that's kind of the scaling behavior. There is just like, yeah, you're basically gonna hit a brick wall, and that's that. Like you're either gonna get the frequency you want at a relatively reasonable voltage, or you're not gonna hit that frequency at all. So that makes things nice and simple, in my opinion. Now, if you care about efficiency, you probably want to stay below like you want to stay below like 1.2 volts dye sense voltage, I'd say, if you want good efficiency, because you can really like, yeah, and really like this right here is actually sort of like, this is a really big frequency jump for a very minor increase in power draw, right? And you can sort of see that the performance per watt, and even this, like this is a pretty big performance per watt drop. But then once you get all the way up down to here, like, yeah, this is not great. Right, that's what. Which the fun fact, like overclocking always completely just trashes your performance per watt. There's never been a scenario where raising the voltage doesn't trash your performance per watt, and the reason for this is very very simple. Your power consumption is quadratic with the voltage. So if you increase your voltage by 10%, you always get at least a 21% increase in power consumption. And I say at least because typically a increase in power consumption is associated with an increase in operating temperature, and an increase in operating temperature leads to more leakage, which leads to more power consumption. So generally so basically, if you're raising the voltage, your power consumption goes up very, very quickly, and if you're lowering it, your power consumption goes down very, very quickly. Because it's literally like V squared, or well, percent increase in voltage squared, and that gives you your increase in power consumption before accounting for other effects. Also, when you raise the frequency, that causes a linear increase in power consumption. So, you have the linear increase in power consumption from voltage, from frequency, stacked on top of the quadratic power consumption increase from voltage, and then also the temperature effect is not some weird nonlinear thing. So I'm not. I think it's exponential. And so you stack that with, you stack all of those effects together, and overclocking always does this to your performance per watt. Like, we went from like 48 points per watt to 31, which is like, that's like, I want to say that's like a 40% drop in efficiency. So that's great, but yeah, that's just kind of overclocking for you. Anyway, so that's the P-core scaling, and yeah, if you care about efficiency, you probably want to stay basically like below 5 gigahertz. I don't know, like on one hand, like that's not really going to hurt you that much just because the P-cores are so insanely fast. On the other hand, I'm not sure that you. The funny thing is, like, the stock behavior of the CPU is actually really bad in terms of how much extra voltage it runs on, which is normal. Like CPUs, GPUs from the factory, they come with a whole bunch of, extra voltage for the sake of maintaining stability, even on the world's crappiest motherboards and power supplies. And so the thing is, like basically this is a lot lower power draw than what a like if I left the CPU stock at 5 gigahertz, it would be pulling a hell of a lot more power than it does here in this testing. Um, but yeah, so maybe a sort of efficiency focused manual settings might make sense. I don't know. Like you would certainly be saving power compared to running the CPU at stock, I think. Um, Anyway, let's talk about the E-cores, or error cores as I like to call them. And the reason I like to call them error cores is because of what they do to the ring clock. See, the E-cores live in these clusters at the end of the ring. And this cluster here has one connection to the ring. And the ring is this part of the CPU right here. And that connects all of your cores and all of the L3 caches to like your memory controller and the PCIe and everything else, right? So this is basically Intel's, like the Intel equivalent of the AMD Infinity fabric. And so the faster you have, like the more ring clock you have, the lower your memory latency is, the more memory performance you have. And so any memory intensive workloads or memory starved workloads, they're going to benefit from higher ring clocks. Also, anything that does like a lot of core-to-core communication would also benefit from higher ring clocks, though I've not really looked into that too much. And I guess most of those workloads would also generally look like they're memory starved anyway. But yeah, so that's kind of that. So that's the ring. And the E-cores all share just like one connector to the ring. And that connector evidently runs at the ring clock and sucks, because the moment you turn even a single E-core on, your ring clock goes straight to hell, which really isn't that surprising because the E-cores and consequently, like I'd say probably this entire portion of the CPU, right? Like the iGPU E-core section of the entire chip, this whole section of the chip is there for laptops. I would assume it is optimized for max performance per watt rather than, or more like not even performance per watt. It's optimized for low power rather than high performance. And so consequently, which I don't think the ring itself is going to be optimized like that, or the L3 caches in the area. But whatever ultimately connects the E-cores to said L3 caches and the ring, yeah, that's probably designed for like low power consumption, because it just trashes the frequency the moment you turn on a single E-core, and the E-cores themselves really don't clock that high. And yeah, even at high voltages. And that's the other, that's the funny thing with the E-cores is like the E-cores will actually scale to higher voltages than the P-cores, probably because they run at lower temperatures. But I highly recommend you don't do that, because if you look at this right here, right, if you go from 1.35 volts to 1.4 volts, you increase your power consumption by 33 watts. And if you do that just for the sake of increasing your E-core frequency by 100 megahertz, it's really not going to make much of a difference to your overall multi-threaded performance, but it's going to significantly increase your power consumption, because the E-cores and the P-cores all run off of the same V-core power rail. So yeah, I just like I guess if you have workloads that would be better suited to running on a 5950X, I guess not like well, no, like I would not do this, because you're going to have a hell of a time cooling it. Like this is already hard enough to cool as is. And so the way I would approach the E-core overclocking is max out your P-cores, and then whatever the E-cores happen to do is whatever you stop with. Like I wouldn't put too much time and effort into maxing out the E-cores. They don't really go that, like they don't go that high. They just scale with core voltage anyway, so it's like there's no like, oh, you can do this to make the E-cores clock higher without massively increasing overall CPU power consumption. Like, no, the only way you're getting the E-cores to clock higher is if you blow out your power draw on the P-cores, which is dumb, because those already have, like, they already pull a ton of power. They already run kind of hot. I don't know why you'd want to make that worse for, marginal improvements in multi-threaded performance. So, yeah, so that's kind of the E-core scaling there. And also they just scale terribly, right? Like you need tons of voltage for each each 100 megahertz on the E-cores. It's not really that surprising. Again, they're like, these as far as I'm concerned, like they're laptop cores. It literally, like the name tells you, right? Efficiency cores. In other words, laptop cores, because laptops got batteries and batteries run out. So you need good efficiency for those. Um, and so, yeah, like expecting them to clock high, well, they don't. Expecting them, so yeah, that's kind of that with the E-cores. And personally, I would just turn them off. Because especially if I was doing a game, like, yeah, for my personal system, like I think my current setup, I don't think gets this much Cinebench score, or even this much in R20. Um, and like this is a lot of multi-threaded performance, right? Like that is a lot of multi-threaded performance. That's like more multi-threaded performance than a six-ish, like that's like 6 GHz 10900K. Like that is so much multi-threaded performance. That I really like. I don't see the massive downside there. Like, yeah, it's going to be less than a 5950X or a 5900X, but I'd say most people probably don't need that much multi-threaded performance, right? Whereas there is a lot of workloads that will sort of just hit memory bottlenecks. And so, I would prioritize ring clock over multi-threaded performance on a 12900K because it's like it's not lacking that if you only have the P cores turned on. And this is doubly true if you have a 12700K because you've got even less E cores to begin with, so much less of a loss when you turn them off. Though it is worth noting that the 12700K should on average have worse silicon quality. So, yeah, like I'd say 12700Ks probably don't do 5.2 gigahertz for Cinebench R20, just in general. Um, but yeah. Anyway, so where was I going with this? Right, yeah. So the E-cores they're just kind of there. I like them about as much as I like the iGPU, which in other words means if it was gone, I wouldn't care. Um, yeah, like I would have really preferred if Intel had given us a 10 P-core CPU, which you can see clearly right here why the E-cores exist, right? Like this is 184 watts, 10,000 over 10,000 points, whereas a 10 P-core CPU would theoretically put like 9,300 points at around 190 watts power draw. So yes, this is more Cinebench score for slightly less power draw. In fact, it's about like a 10 P-core CPU would have 8.4% less multi-threaded performance than the 8+8 configuration we have right now. But 9,300 points in Cinebench R20 is still a ton of multi-threaded performance, in my opinion. So it's just like I don't see the massive, like I don't see the big downside there, unless you're in a laptop environment. In which case, yeah, okay, I can totally understand if you're in a laptop this slight improvement in power efficiency, which I would assume at lower frequencies and lower voltages, the E cores probably are even more beneficial. Yeah, I can see why you'd want the E cores for that. For laptops, but for desktop, I don't really see the point in them. And one thing that I've seen people say is like, oh, you can put background tasks on the E cores, and it's like you do realize if you had 10 P cores, you could just take one of your 10 P cores, put all of your background tasks on that 10th P core, and have all nine, the remaining 9 P cores for whatever else you're doing. Like, like how many background tasks are you running that you need you need 8 kind of crappy cores to deal with them. Um, right? Like most background applications are going to be using maybe like 5% of the available clock cycles on a P core. And that's a lot, to be completely honest. Like 5% of the available clock cycles is a lot. And that's incidentally how Task Manager monitors CPU usage. It monitors how many clock cycles are being used, not how many CPU resources are being used. So that's why, like, if you run a memory stress test, it tells you that the CPU is being used to 100%, even though the CPU is actually spending most of its time waiting for memory access, and it isn't pulling much in the way of power. But anyway, yeah, so like I would have preferred like for desktop applications, I think a 10P core CPU would have been better. You wouldn't have you wouldn't have the ring penalty. It still wouldn't clock as high as the 8 core configuration just because the more cores you have on the ring, the like harder it is to run the ring. Like the more things the ring has to connect to, the slower it runs, but the the E cores are like really bad for the ring clock. Like you turn them on and the ring clock goes straight to hell, which yeah, that's an E-core thing. As far as I can tell. That really seems to just be directly caused by the E-cores themselves. So I would assume if you had a 10P core design, you probably wouldn't be able to run like 5 gigahertz ring, but you would maybe be able to do like 4.8 or something. Actually, you probably would be able to do 5 gigahertz ring. And the reason I say that is this right here is actually limited by the CPU frequency and not the ring clock. Because um, on the Gigabyte Z690 Aeros Pro, the current BIOS version, there's a bug. You can't turn off the ring to core down bin. So the ring cannot be equal to the core clock, and I can't run the CPU above 5.2 gigahertz, therefore the ring cannot be above 5 gigahertz. If I'm going to be stress testing with Cinebench, which Cinebench is not a real stress test, so for actual real world workloads, like, well, for actual stress tests, I'd expect the ring clock to drop down to somewhere in the range of 4.5 to 4.7, but that's still a hell of a lot more than the 4.2 you get when you just turn the E-cores on. And also, I think this would probably come down if you checked with an actual stress test instead of Cinebench. So you might actually be limited to like 4.1 or 4.2 ring if you were actually doing a stress test, which is just like, yeah, this is not great. It's just generally not great in my opinion. So yeah, I do not like the E-cores. They're about as useful as the iGPU in my opinion, which, yes, there are certain scenarios where the iGPUs is very helpful, and then a lot of the time I wish I didn't have to pay for it. But the vast majority of the time, personally, actually all of the time for me, I'd prefer if I didn't have to pay for the stupid thing being there. So yeah. Anyway, that's sort of the overclocking behavior of the ENP cores of the 12900K. You should see similar behavior with basically all the other 12th gen CPUs. Just, expect the frequencies to be different. You're not going to be hitting the same kinds of frequencies as I am here, unless your CPU is like the same level of quality as mine. And yeah, that's it for the video. So thank you to Gigabyte for providing the hardware. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, the usual YouTuber merch. Both Patreon and Teespring help out immensely with running the channel, so it'd be much appreciated if you check them out. And that's it for the video, so thank you for watching, and goodbye.